All right, let's get right into it. Today, we're basically becoming algebraic detectives to solve what I like to call the case of the missing point. We're going to dive into a really cool part of rational functions that, trips a lot of people up. But trust me, once you see the trick, it's actually super straightforward.
Okay, so let's start with a question we've all heard a million times. When you have a fraction, what's the one unbreakable rule? Right, you can't divide by zero. But when we're talking about graphs, what does can't do that actually look like?
Well, most of the time, when that denominator hits zero, you get this giant invisible wall called a vertical asymptote. The graph just rockets up to positive infinity on one side and plummets to negative infinity on the other. It gets closer and closer, but never, ever touches. This is our usual suspect. But here's the plot twist. What if the little piece of the equation that's causing all that trouble, that zero in the denominator, has an identical twin up in the numerator? What happens if you can just cancel it out? Poof, it's gone. Does the asymptote just disappear with it? That is exactly what we're here to figure out.
So here's our plan of attack for cracking this case. First, we're going to meet the asymptote's sneaky cousin. Then, we'll actually define what a hole is. We'll go through a 5-step hunt to find them, and then we'll do some examples. After that, we'll look at the common traps people fall into, and finally, why any of this actually matters in the real world.
Right, so a zero in the denominator almost always means a vertical asymptote. But, like we said, we're on the hunt for something a little different, a little quieter. The case where that zero does not create an infinite wall. Okay, it's time to give this mystery a name. What are we actually talking about here? Let's get the official definition on the books. So, we call it a hole. The fancy term is a removable discontinuity, and honestly, that name says it all. It's not some giant infinite break in the graph, it's just a single tiny point that's been plucked right out of a line that would otherwise be perfectly smooth. The graph just kind of hops right over it. This table really breaks it down. Look, for a vertical asymptote, the factor in the denominator sticks around. It does not cancel. For a hole, it absolutely does. With an asymptote, the graph goes nuts, flying off to infinity. With a hole, the graph just keeps on going, except for that one missing point, which we show with a little open circle. So how in the world do we find these invisible little points? I mean, you can't just look for them on your graphing calculator. It won't show them. You need a process. You need a detective's toolkit. And lucky for us, there's a foolproof 5-step hunt that works every time. Here it is. Step 1, you factor everything, top and bottom. Break it all down. Step 2, you spot the common factor, the one that's in both places, and you cancel it. Step 3, take that factor you just canceled, set it equal to 0, and solve. That gives you the x-coordinate of the hole. Step 4, and listen up. This is the most important part. You plug that x value into the new simplified function to get the y-coordinate. And finally, step 5, you just write down your answer as a point, xy. Okay, that's enough theory. Let's see how this actually works. Time to roll up our sleeves and solve a few of these cases. Case file number 1. This is a nice, easy one to start. The function is already factored for us, so the culprit is basically hiding in plain sight. You see it? Yep, it's that x minus 2. It's on the top, it's on the bottom, so see ya, we cancel it. Now we take that factor, x minus 2, set it to 0, which tells us our hole is at x equals 2. Then we take that 2 and plug it into what's left over, the simplified function, which is 1 over x plus 3. That gives us 1 over 5. And boom, case closed. There's a hole at the point 2, 1/5. All right, on to case file number 2. This one's a little trickier. It's in disguise. We've got a quadratic up top, so our first move is obvious. We've got to factor it. So that x squared minus 9, that's a classic difference of squares, right? It factors into x minus 3 times x plus 3. And would you look at that? There's an x plus 3 waiting for us in the denominator. They cancel out. We set that canceled factor, x plus 3, to 0 and get x equals negative 3. We plug that into our simplified function, which is now just y equals x minus 3, and we get negative 6. The hole is at negative 3, negative 6. Simple as that. Okay, last case, and this one's the big one. The instructions are to classify all the discontinuities. That's a hint. It means we're probably looking for a hole and its rowdy cousin, the vertical asymptote. So we factor everything. The top becomes x minus 3, x plus 2. The bottom becomes x minus 2, x plus 2. Aha! The x plus 2 is our common factor. It cancels. That means we have a hole at x equals negative 2. But hang on, what about that x minus 2 factor left in the denominator?
It didn't cancel out, did it? So that means it creates a vertical asymptote at x equals 2. And this example shows it all perfectly. The factor that cancels makes a hole, the one that's left over makes an asymptote.
Now that we're experts at finding these things, let's talk about the traps. Because every good detective knows you have to anticipate the common mistakes that can completely mess up an investigation. Here it is, the number one rookie mistake I see all the time. A student finds the x-coordinate, say x equals 2, and they think, awesome, I'll just plug 2 back into the original equation they gave me. I mean, it sounds logical, right? It's totally, completely wrong. Just think about it for a second. The reason that x value is special is because it's the number that makes the denominator of the original function 0. So if you plug it back in, you're always going to get 0 divided by 0, which is undefined. It doesn't tell you anything. You have to use the simplified function to find where that point would have been if the hole was filled in. So let's just hammer this home. Trap number 1, never, ever use the original function to find the y-coordinate. Never. And trap number 2, don't even bother trying to find these on your graphing calculator. The pixels on the screen are just too big to show a single missing point. It's an algebraic idea, and you have to use algebra to find it. Okay, we cracked the case, we found the missing points, we avoided the traps, but let's zoom out for a second. Why should we care about these tiny little holes in a graph? Does this stuff actually matter outside of a math class? Oh yeah, it matters. This is where it gets really cool. In the real world, in fields like digital signal processing or data science, a removable discontinuity isn't just a math problem. It's a glitch. It's a tiny blip of static in an audio file. It's a single bad pixel in a digital photo. And engineers use this exact same algebra to find those holes and then mathematically patch them to fix the data, giving us a clean, smooth signal. So think about that. These tiny, invisible holes that we have to hunt for with algebra are actually patched up glitches in the music you listen to and the pictures you see. It really makes you wonder, doesn't it? What other invisible details, what other secrets are hiding in the math that builds the world all around us? Thanks for watching.